not a bit like yesterday. There's again some instruction in this Python notebook. Again, you don't have to run the notebook. It's just convenient to display a lot of information. You can run the scripts individually. I've made some updates yesterday. So if you pulled the thing yesterday, made some updates last night to some of the scripts, make things work a bit better. So if you do a git pull, probably you just get a slightly better version. So what are we doing today? So yesterday we played just 2 halos, just to make sure we can download the code, compile the code, run the code, and make some plots. Today we are doing about the same thing, but slightly more complicated, and maybe slightly more interesting. So the idea is that what we're going to do, we're going to do a full simulation from starting from first principle and then all the way to having some results that we can look at for a cosmological simulation. So one thing I didn't talk about much this morning, because it's part of the afternoon session, is that one of the key components of the lambda CDM model is that we assume that we have what is called the Gaussian random field. So this perturbation as a start, they are assumed to have a specific shape and a specific distribution. So they all have different sizes, and they are given by a Gaussian shape. That's been tested very well. So what we're going to do here, the first part of the script is just going to generate some Gaussian random field, look at what they look like, then the same thing, but with a specific power spectrum. So the fluctuations, remember, yesterday we saw this cosmic background power spectrum with these different wiggles and shapes. So if you turn this into, if you ask what is the math power distribution, you can calculate what is the power spectrum, how many waves of different sizes there are. Right? And typically we find that for a large range of wave size, it's like the power spectrum is almost like k to the -2. So we're going to generate some Gaussian random field with a specific shape, so we know what this looks like, and we're going to just make a small map. So looking at, if I started some fluctuation with a specific power spectrum, so I would start a bit of universe that has this level of fluctuation. You can verify that indeed everything is Gaussian and it has a specific power spectrum. And then what we're going to do is, so we could use something like that, but that's a bit boring, or we could use something which has slightly better, more realistic. So one of the things we downloaded is some initial condition with some lambda CDM parameters, and then we're going to run the simulation. So yesterday how to run the code is going to be the same here. There is a directory for simulation in which there is a submit script that you can copy the line in and then run the code. I think it takes about, last night on my laptop, it took, I think, 15 minutes to run, 20 minutes. So I don't know how good these are, probably about the same. Right? And then the idea is that we can then start either making, the code will produce files with power spectra, which we can look at and see how the matter power spectrum evolves, or we can also have some of the scripts at the end, so the text is very long, you can read through it and ask questions, of course. But the goal is that we're going to get some bit of universe that should look like that, right? Some empty regions, some halos, maybe some filaments. And then what we can also do is, because we're going to have multiple snapshots, is that we can do, I doesn't look very good on this, but we can look at how it evolves through time. So here I've just done different slices, but if you just put them one after the other, it can turn into a movie, and it will look something like the movie that was trying to show this morning, and it didn't look very well. Okay? So that's the goal for the afternoon. In principle, all of the instructions are in here, and as usual, I've probably forgotten something. So just ask if something doesn't work, and ask if you need some more questions about the physics, the simulation, or whatever. And otherwise, have fun. Okay. So I mentioned just before, I've made some updates. So if you pull the repository yesterday, do a git pull first. So there'll be some small updates to some of the scripts. to make things work a bit better on the machine here. So we listed it. Oh, okay. Can you read it or can we read it? No, I can read it. Yes, so the start is the two dimensions. Yeah. Okay, so the start here, the idea is that, right, we discussed yesterday, if we go very far in time, we have an almost uniform distribution of gas and dark matter, and it has tiny fluctuations. And then the question one could ask is, what is the shape of this fluctuation? Because it could just be, are they very correlated? Are they very large? Different modes. So, for different arguments coming from quantum physics, we expect them to have a Gaussian distribution, meaning that the size of the peaks will if there's a very large fluctuation, they are much more rare than a small fluctuation. And so, and that's not just from theory, we can also actually measure that. So if you have this map of the cosmic quantum background, you can check how the peaks are distributed. So the first part of the script here is just to give us some idea of what this looks like, so we can have some mental picture of what this represents. So what we do first is just in 2 dimensions, but what we propose to do is to essentially generate just a grid of points, right, that have the value of each pixel is taken from a Gaussian distribution. So at every point, I'm going to draw a random number, and that random number, instead of just being uniform between, say, -5 and 5, is going to be with a specific mean. So here 0 and a specific sigma. So I'm drawing from a Gaussian, and then each pixel is completely independent from each other. So now I get a map like this, which, given that it has the mean of 0, so this is what we call the white noise field. So it's random noise. There's essentially no information in there. But that's a good starting point for some sort of realization of a Gaussian random. So that could be saying this could be some sort of initial condition. But that is not exactly what we see in the data. It's also not what we want. So one thing we can measure from that is to, first of all, so we got Python to generate some random numbers. So we suspect that should work. But the first thing we could do is just verify that indeed, if I plot a histogram of all of the pixel, I indeed get a Gaussian, check that actually I have a Gaussian random field, which if I look at, that would be the middle picture here. So just what I've done in this, as you can see through this piece of script in between here, is just a histogram of all of the pixels. And indeed, it's a Gaussian random field. No surprise, this is what we wanted, but this is what, that's one way to verify. So if I give you a map of the cosmic microwave background, to just do a histogram of all the pixels and see what is the mean in the schematics, whether they're actually Gaussian distributed. Now, the other thing which is important, which we haven't touched here in this first example, is that we have not input any, so there's no information on all scales. There's no correlation between any of the pixels. They're just, each pixel independently is just a random draw. Right? There's no correlation at all. And so what we can try to measure, we can measure the power spectrum. So see, are there any, so if I take the Fourier transform of that map, and see whether there are any correlation between different scales. Right? And what do we expect? We expect there should be no correlation because we're drawing things completely independently from each other. So what we can do is measure that. And so the other part, sorry if that's script here, is going to measure here. So we do a Fourier transform. Up here, it's like FFT, so FFT2 is because it's in 2D. And then we measure the power spectrum, and we find now on the bottom right that indeed it's flat. Normalization is sort of arbitrary. It's flat up to some fluctuation because it's one realization. I was lucky or not when I was drawing my random numbers. If you run yourself, I'm sure you get a different shape every time you get a different shape. But telling us there's no information on any scale. All of the scales have the same chance of being drawn by our random numbers, right? Because that's exactly what we wanted. But there's also no cosmology information. This is just a pure, random white noise Gaussian random field. Yes.
So this is just the
Yes.
So this next part is where we will come to.
Yeah. So in the first version, so here we just said there's no correlation between any of the scales, right? But this is just white noise. What we want is that in reality, that we saw yesterday, I showed you this picture of the different amplitude of the modes in the cosmic microwave background. And so we know that different scales are correlated in different ways. So there is the power spectrum in the real universe. This is not a flat line. So what we want to do is modify our power spectrum such that we reproduce so that there are different scales are correlated.
This correlation is like the falls, but it isn't there. It's the same as unknown.
I don't understand your question.
Of here,
Yeah, so here we generated some random pixels. No, you're just correcting. You're correcting the initial map. Yes. We could generate a new map if you want.
that's why
Yeah, we do a different one. Yes. But all of them, because they're all statistically valid versions. So if you just say I want Chelsea with this R spectrum, every time you realize the map, it's a valid realization of this bit of universe. Okay, so why is more realistic? So so first of all, this is because of what we observe. So if you take a picture of the cosmic microscope and ask what is the amplitude of the different modes, you realize that it's not flat, that certain modes, so the K scales, have larger amplitude than others. And it turns out that, at least for a reasonable range of values in K, it looks pretty much like K to the minus 2, which I think is what we are doing here, yes, K to the minus 2. But if you want to know exactly what is the combination, so that will, so the K to minus 2 is an approximation, so that will be this dash line. This is not what the real universe is like. It's not K to minus 2 over all ranges, just in this narrow range in K. The real one has slightly different shapes and very large K. There's plots later on of the real one. This is for now. Yeah, that's more like it. And so it has different shaping patterns, actually different growing, actually goes back down. And these are the exact shape of that is set by your choice of cosmology. So if you add more matter or more barons or more lambda or change other things, that initial power spectrum will have a different shape. Yeah, so the other one is a more real one here, but this one has a very complicated shape. Whereas say, well, look, this bit here is like K to minus 2. So let's just K to minus 2 for the example above. Just rescaling.
This is supposed to be different.
Yes. Yes. Okay, so the vector K here are different, so it's a Fourier transform. So these are the different modes that you can have. So we have a difference between size. And so then what we have in the first mode is 2 pi over that length, and the next one will be 2 pi over so it will be. So the question is, the case corresponds to the different wavelengths, the sine wave you can have in that box. Because the first one is one we have one sine wave, the second one we have 2 oscillations, and this one. But now because we're doing this in 2 dimensions, right? So there's a few Fourier transform with one dimensional function that you have. This is just one number for each wavelength. But here, because it's in 2D, you can have it's a vector, right? Because you could have one long sine wave in this direction and one vector in this direction. So we represent this vector. Okay. Was a question? Yes, that's the idea. Right, but that's not a power spectrum. Well, okay, it is a power spectrum to an extent, but this is here what we're looking at. So the one we're looking in the example of the big screen, this is now the Fourier transform of so here square, but you can think of it as being Fourier transform of something infinity in Q. This here, these are not, it's not quite a Fourier transform, although it's the same spirit, but these are like spherical harmonies, right? Because this is what we're looking at here. Remember, the map shows what we are, is like us being inside a sphere and looking more around us. So instead of doing a Fourier transform, what we say we can do expansion in spherical harmonies. You know what spherical harmonies? Like when you do the hydrogen atom calculation, right? You have different powers. That's exactly what it is. And in the case of the cosmic microwave, it makes more sense because we are inside a sphere looking around. So it's like a more natural way of describing the different ones. So now there's a way of converting it from one to the other, which I don't remember. It's very complicated. That's it.
It has like, do you have this as
Does this make sense?
But
So,
so looking at this,
Yeah.
yeah.
no, it's the same amount of information. It's just a different way of representing the data.
Or it's easier to see just by the.
Here it's easier because what you want to do is just want to look at a specific map. But if you want to do a simulation or if you want to talk about a region of the universe which is not just a plane sphere, it makes more sense to go to plane like planes. It's a more natural way of describing it. Because this is not 3D, right? This is really on the surface of a sphere. Now if you're going to look at the distribution of galaxies or things, they are in 3D, so they're definitely not on the surface of a sphere because you also have the radial directions. So you have to do something more here. It's just easier to just think about normal XYZ coordinates. It's easier. Just like one question. 1 second. Yes.
When I check to run the simulation, we identify these.
Okay, so you don't have this. You need to install this type of side.
We that they
Okay. For the lead GSL. I tried the no try lead.
okay. Yeah.
Remove GSL. LID. GSL.
In capital,
Also level. Dash. Yeah.
the
Yeah, that's true.
that's
it.
Yeah.
I think that you need to configure the code. Configure when you run. So when you install yesterday, you installed the code. And you did something like configure and then make.
In
Yes. So that now you need to configure again to the right column. GSL this.
okay.
Yes.
The same.
Same thing. Okay. So you need to so if you're missing the simulation code, you may be missing some library that I think I'm not sure was listed but you probably need to if you're on an Ubuntu-like system, you need to install something called lib gsl-dev. So if you do apt get installed, I think on the machine here should be installed. And then after that, you need to redo configure and then make.
Is main dash J.
That's just making it faster. If you do J something, it tells to use more of the CPUs. Okay, so if I come back to the script, so here we generated a random field which has no power on any scale. But we saw yesterday that there is a lot of information in the cosmic microwave background. Not all of the fluctuations are the same level. There are some bigger and smaller fluctuations. This is also how we know something about the lambda scale model, but it's also the other way around, because the physics, essentially the physics of the model tells us how big the different peaks should be. And in particular, so that is in spherical harmonics, but if I go into 3D XYZ coordinates, that will tell me that there is a power spectrum that's not flat, not all of the scales are the same level of amplitude. So there are some fluctuations in the density field on some scales which are larger than in other scales. In particular, we should get And if I look at the real power spectrum, it looks like that. So that's just for a set of scales. So if I go, so K, remember this is this amplitude, this is K is the size of the sine waves, right? We're thinking in Fourier space here. So on the left, for small k, it means large waves. And then large k means small waves with small oscillation. And so there is a specific shape, which again depends on the exact set of omega lambda, omega matter, omega baryons, and all of the other parameters that this power spectrum will take. This is only just a small region here. But if you keep going, it just keeps going. So the fluctuation gets smaller and smaller on when they get smaller in space. And then actually on the other side, it comes back down at some point as well. There's no really big, large wave, right? And so the one we generated just using the one-line Python Gaussian random thing was a horizontal line, which we don't like. So what we usually do when we want to generate a starting point of a simulation is that we generate a random field, we measure its power spectrum, and then we correct it. Okay? So in particular here, because to keep it simple, we can cheat and say, well, look, in this region here, this looks like k to the minus 2. So as an example, what the bit of code that is just above does is it takes our input, so we have our input here, right? We calculated this power spectrum, it's almost flat. And what we say is that I'm going to correct my wave, my amplitude, to make it that when I run the same thing again, it's still Gaussian, but the power spectrum on large scale now has larger modes, has more amplitude than on small scale. Right? And you can see visually it looks quite different. Now it looks like there are regions that are, there's more correlation. There are more larger yellow region in the previous one. The previous one is really very noisy with no information, right? If I just swap back, this one looks very much like there's nothing in there. But here now, there's clearly something happening. There are bigger yellow regions correlated with each other and so on, and like bigger blue regions and so on, right? So now we have actually changed the initial power spectrum of our Gaussian random field. And so what we would do in reality, if we had now if we want to do a real simulation, so first of all, we do this in 3D, not in 2D, but then it's easier to see in 2D for the exercise here. And instead of just taking k to the minus 2, we would take the real one, which is this more complicated shape that I'm showing here. And then do the same exercise of generating a random noise, calculating the Fourier transform, and then correcting the modes until they look like what we want. So that would be what is done on this simulation. And then what this exact shape depends on? Well, it will depend on all of the different parameters of the model. So for omega matter, omega lambda, depending on omega baryon, it will depend on the amplitude of the power spectrum, it will depend on sigma 8 and on all of these other parameters. And so the good thing is, because it's very early universe, right, the fluctuations are very, very small, we can calculate this light perturbation theory. I explained yesterday that we can't do the late time universe light perturbation theory because it's not perturbation anymore, the fluctuations grow. But in the early universe, we can do the calculation almost natively. And there are different codes that do this, and that usually the ones that I use to analyze cosmic microwave background. Right? And there are two famous codes. One is called CAMP, the other one is called CLASS. And those are two codes that calculate for you. You give in as an input all of these, and whatever other modifications. There are so many modifications that people have done already for all kinds of other theory they have of cosmology. And then out comes something like this power spectrum here. So that would be power spectrum for a specific set of parameters that we have. Okay, same thing. So you probably need There might be a fluid here, I'm not sure. Let's see what Ubuntu says. So, I can try to do this week after the weekend.
So how many steps have to be simulation?
Same question. What we said they are. So what the this call here is redshift.
I start to.
It's going to go to redshift 0.
You just start streaming.
Start at version 27. Okay. But it should be, if you open another terminal, they should already be writing some snapshots. So you can already start. Sorry. Okay. They should already be writing some outputs. It's not just at the end, right? So if you're doing, yeah, so there are already some snapshots at different times. Yes. Yes. Support, yes. Also, already is an also support for the machine. Just missing one of the libraries. there's something in store. So it's not strange to it. Okay, so what would be the next step, right? So the next step would be once we have a bar spectrum, and we know what we want to do is then generate a bunch of particles with their positions such that when I take the Fourier transform, it looks like that. Right? That's a relatively difficult step, so we're not going to do this. It's a bit conceptually not very difficult, but a bit of coding is a bit annoying. So what we do instead is that I think if you download the repository, is that we provide you with some initial conditions that have already the correct power spectrum implemented. Right? So there's this file ICs swift.hg5, which is HG5 is the format we use for the snapshot, but it's essentially telling it's a list of all of the particles with their position, their velocities, and their mass. And then what you can do is that you can load that file. Just want to look at it. We looked at yesterday, you looked at the halos. It's the same thing here. You show that it's going to be very boring because there's no information. This is a redshift 127 when we start the simulation. And so everything looks like it's almost like a grid. Right? Because the fluctuations are very small, but the particles have moved by a small amount compared to a perfect grid. And that small amount they have moved by is given by this power spectrum. So if we take a Fourier transform of these positions, we should get back something like the power spectrum we want. So that's the initial state. And then what we do, right? So if we take a Fourier transform of that thing, you get this blue line. So it's not perfect because we draw some random numbers. It's not always going to be exactly what we want. But in the region we care about, it's almost on top of the dashed line. So what we have here now is that we have generated for you some initial conditions that have power spectrum with interesting information. And so what we want to do next is since we have a starting point, is then to run a simulation. Okay, so I've seen some of you already running things. So if you go in the simulation directory, there is a run, I think submit.sh, I think it's called, with a line telling you how to run the simulation. And then you can run it and see the different snapshots. So when you run the code, you'll see it's printing out a lot of numbers. You'll see one column. The first column is the number of the step, and then there's another. I think the third column is a number going down. That's the current redshift. Fourth column. So the fourth column is the redshift, so you can see the number going down as the simulation moves toward the top. Yeah, I think it does total.
Why at the beginning for big redshift and the simulation goes up? I mean, from 127 down to 105. Then I have a set of in the second decimal.
Yeah, what do you think?
Because when we say close to the simulation, there are more, there is more. When we get closer, the calculus has to be more, have better precision.
Yeah, so there's a bit of that. Okay, so there are two reasons. One is redshift and pi is not a linear function of each other. And so, for instance, between redshift 1 and 0, it's about 8 billion years. And between 2 and 1, it's 2 billion years. And between 1,000 and 900 minutes, 5 minutes. But like, it's very short amount of time. So if you say I want my delta t to be fixed in time, then then you do bigger jumps in redshifts at high redshift than yours. There's that. It's the most important part. And then you're also correct that having early research where everything is very uniform, everything is moving very easy. It's like very linear. There's no the trajectory of all the particles that are simple. So we can do longer sets. And then at late time, we start having halo particles moving around each other, like in the galaxy or something. Then you need to be very precise. You need to do a lot of steps to do an orbit for it. Yes. Because we talking about the numbers with a mean of 0 and a standard error. Okay, so if you recognize the mean of this being over density, so it should be the mean density plus or minus that's the difference. Okay. Yes. But that's the problem I have on the board. This is your own machine, right? No, this is this machine here. Yes. So they have this. So no, there's nothing you can do. It's telling you it's missing this library. You don't know why it was T has. Where did it configure? Yeah. Okay. Yesterday it configured. Or today or what? It's a different machine. Okay. Right, so on this machine you need something like the configure. And then they didn't find that library. They didn't find it. So okay, just on this one it works.
Yeah, the problem is.
But this one is missing another one. So can you do So where did you do the configure set? Did you go to the directory where you did that? Yes. Oh, the order. When you do this backslash nothing else. Something that wasn't installed on the machine yesterday. I don't know. Yes. Okay, so what did you do? What about this? Exactly like in the submit? Yes. Yes, good. But I think when you configure, you should have enabled. What is the saying that when you open that submit file? Yeah, can you open it? Just
Which one?
this one. Just gedit or Emacs. Then any editor. Gedit. Right. So okay, you should have configured this. Either you configure with this, or you remove this.
I didn't.
Okay. Well, can you open it? Yeah.
No,
You can just copy that line instead of typing. So
o sea, le puse
copy and
actualicé,
paste that in the terminal.
tweets, no sé qué, no sé qué. Pero no, ya había en configure off, pero
Okay, and that's so you're missing
es que están ahí archivos
so you're missing the library called the second language. I think you will have to configure again so that it okay, now it's this file so you have to be directly where the file is. Oh, so when you downloaded the book? Okay, don't need the tutorial. Can you go to the you're the one that's
We are trying to rewrite stuff.
So I think on this one is GSL, which is missing. Sorry. I don't know if trying with another machine.
No, llegamos está condición periódica.
So the first collaboration. So after install, or get it. No, get and you need to install the first tool. Then you probably have to configure and manage. What do you mean by Yes? Yes.
We create.
It depends what you mean. Okay, so the whole universe at some point was very dense. At some point, the whole universe started studying as density photons and stuff. Right? That is everything. We are at somewhere in that soup somewhere. Right? We are here. But that happens everywhere at the same time. But now, photons very far away started traveling. Okay. Like everywhere else, also the photons that appeared where we are now, they also started traveling, but they moved away from us. These we have never seen, they have just moved away from us. But photons which are far away, that started 30 billion years ago, very far away from us, and they went in all directions. These we see now, but we see these from all the other positions around us. Right? So we don't see the photons from our bit of the scene. These we will never see them, they are gone. Right? We see photons from every other bit on the sky, from every other region, far away from us. So we're not in the sea. So to answer the question, we are not in the sea. Our atoms are not. They are not in the CMB that we see, but they are in the region that when the CMB was emitted, was doing the same thing, but the photons were gone. They are going somewhere else. Yeah. So you're seeing the photons from the same time, but we are moving forward in time. So they come from further in past, but they're still from the same. If you say t equals 0 with the Big Bang, when there's t equals c, that distance doesn't change. But we move further and further and further away from that time.
when we do the series, we do yesterday.
One from the months ago. It's not. But so if you could see really tiny situations, you could see different programs that we see very large scale. So the bits of CP we see are so large that they don't change over a day or even over 100 years. We do not see a difference. We don't have enough detail to see it. Yes. Well, it's for we know exactly. We can I forgot the exact number, but you can calculate, given the temperature of the CD and given the density of the universe, how many photons per cubic centimeter there is that come from the CD. I think the number is 400. But so that's something we can calculate. Because we know exactly how many. So you know the density of the universe at the time of the CB. So we know how many protons there were, how many electrons there were, and for each of them, when they position, they will emit a photon. So we know how many photons there are there. The universe expands by a certain amount. These photons, okay, some of them get absorbed, but most of them have been traveling forever. So the number of photons is observed, but the volume of the universe is a lot bigger. So you can calculate how many photons. Right? That also tells us what temperature and everything.
Because the CNV so much waste
No, so what you're saying is that if we now go 10 billion years from now, we're gonna still see CD, but from a different part of the sky. It's further from us.
but in some time
Okay, no. Okay, so maybe you will get, okay, so at some point we'll get less than 1 photon per cubic centimeter. Maybe you will get 10 to the minus 10 photons per cubic centimeter. You always still see some photons. They may be very, very rare, but there still be some. Just very, very far. That is almost true. The question is, how fast is the universe expanding? Right? If the universe keeps accelerating, expands faster and faster and faster, then you're right. At some point, we will not see. Because the distance to the CMB is growing at faster than the speed of light. Right? And the photons cannot catch up. If you keep thinking about that we say all the galaxies are moving away from each other. Okay. So if I make the universe, if I look at the universe in really, really far from now in time, even the galaxies close to us will be moving away from us very fast. And it will be so fast that we cannot get any light anymore from any other galaxy. Because they are moving where it is. Remember this H naught as a function of time, but this is going up. Like so in the very, very long future, all of the galaxies around us will be moving so far, so fast away from us that we cannot see any other galaxy. And then you can look at cosmology. You will never see, you will see our galaxy being the only thing in the universe. And then what you can say, you cannot do anything. All you can say is the theory that says that you can say our universe is just our galaxy. There's no way you can do any experiment to prove this.
Well, at some point, stars are going to go.
That's the more than yeah, so that the universe gets really, really cold. There's no temperature anymore. Everything is dead, and we don't have any form stars anymore. And I don't remember which one comes first. Where are we? Okay, so some of you have started running, some of you have difficulties running simulations, some of you have been running simulations. So in the script here, also tells you how to run things. It's a bit like yesterday, I think there's a submit script and you run the simulation. I told you there's one of the columns does direction, so you see how far it goes. I think it does, the first column is a step number and it does 4,300 steps or something like that. So you can see how far you are. think it says 5 to 10 minutes here to be optimistic. By the end of it, it should have produced, I think, 63 outputs. If I'm not mistaken, there should be a directory for outputs, maybe 67. There's an output, and it has different snapshots in there. And then what you can do, I mean, yesterday you already looked at a snapshot plotting all the particles. So we can do the exact same thing here. So we can load a snapshot and make a dot plot of all of the particles. Now it's in 3D, so I think the easiest thing to do is you don't want to do a dot plot of the whole thing, but you can take a slice and say, I'm going to only take particles between a certain position in Z and another position. Just do a cut, otherwise it's going to get too messy. But we should be able to get an image like that from the simulation. Then that's probably redshift 0. Forgot. Yeah, this is redshift 0. So that's the final snapshot. So yeah. Does it look like that?
But it's not
What you can put in the redshift 0. So if you do, yeah, 0.85, you can add it, you can also add it to the image. So if you make a movie later or something. Like my movie has like a redshift from
with HTML.
No, this is matplotlib, right? So you can Oh yeah, or you can do, if you do a lot of PNGs, you can combine them into a FVEG. That's the Linux tool that makes movies from PNG or from the other thing you can do is, so this is one slice. The thing that can be cool to do is you take that and you can take different slices and make them thirds. So you can turn the box, for instance. There will be the geometry, so you can see the thing from different angles. There's a bit of also almost artist. Did you get work? Oh, this is actually quite awesome. Yeah, thank you. It's faster than my laptop. Thank you. I think the next bit of the script is that you yeah, this kind of thing is a good answer. Yeah, this kind of Well, the first one is just a dot for every particle. This is a dot, and this one is trying to just smooth things and make it a little bit nicer. It's the same information.
Run script here, and this one I don't have permission to run anything.
Oh, but you don't need the
Yeah. Oh, the Jupyter. One is perfect, but I want to run the script. I can find three of the
But it works.
No.
libraries with my try to fix it.
Okay. You need help? Or
It would be good. Yeah, because for example, I downloaded I was just trying to install
yeah.
I downloaded this, but for example, if I try download it,
Yes. Where are you?
It works, but at the end, I don't have the next.
Okay, you're missing.
Right.
You're probably missing.
No.
Yeah, you're missing one of them. Do you have autoplay? You need to leave updates installed.
Wi-Fi is sometimes connect, sometimes not.
Okay, I will try to install automate. Click to just to see whether it makes a difference. And just follow. Okay, well, let's try. It's not many water becomes natural. Because it's missing something.
Todo el mundo lo decía. También lo que vos dijiste que era como la tierra. Claro, son verdad.
I tried to
Yeah, turn on the master. You don't need any permission.
¿Qué es lo que uno dice?
Don't touch configure and then make it touch configure.
Do you see I remember what I, yeah, I don't have the I remember what happened before. I don't have the AC5B.
Ah, okay, that's the problem there. So many people are having this. I don't know why, but it's so much. What you fixed it? I don't know.
Thank you.
Okay, so if you have been able to run the simulation, you should have a certain number of outputs. And the first thing you can do is always the simplest thing is just to make some images. So there's a bit of script in the notebook that you can run. Just one of the snapshots and makes you a map, a density map of the simulation, and that will look like, or it should look like some of the movies I was trying to show this morning. It's just one of the frames. So if you make one of this frame one after the other, you should have a movie of the evolution of that region of the universe. Now, making movies is fun. The other kind of movie you can do is to take one snapshot and just make it turn around. That's also pretty cool. Or you can make, you can fly it through the simulation if you want. Just projection in different ways, depending on how many artistic skills you have. You can do a lot of fun things. The other thing you can do, so this is, we discussed yesterday a bit, right? It's like, okay, we can make images of simulation, we make images of the sky, but how do we compare? How do we know this is, it's not very precise to make just images, although it's fun. So the one thing that the code has also done, it should have generated a lot of files called power spectrum something. Right? And this is the measure of the power spectrum at the different redshift at the different times. So we can see how the quality evolves through time. I think there's a plot even at the end here where we see for the different redshifts how this Fourier transform of the density field evolves. And as we said before lunch, this is something you can also measure in the data. So then if you have different models, you can start comparing your power spectrum prediction from our lambda CDM simulation to some data. So that would be one of the tools that can be used for comparing things if you don't want to just look at images. Although images are fun.
There is a library to make a simulation that
Well, so what you can do is save these images in DHE file or something. This is just a method. So you can save each image in a file, and then the usual way I do things, there's FF in software. And I don't know the other letters. I can write on the board. It's like it's a tool that can convert any movie format to any other movie format. You can also say, take all these images, make a movie format.
based on the stats that.
Yeah, so if you make them 1, 2, 3, 4, 5, the tool is able to understand and put them in that order. So that will also work. You can just make one of the frames or any way you prefer.
Those videos that you show us, they're like driving.
Yeah.
That's so hard.
So
They say.
So here you have these snapshot, you have the 20 position of every particle, right? Forget exactly what, so I think what you do here is you make a slice. So to make these purple images, the script cuts the time channel in the direction, and then we just project that. So what you can do is you can do many different channels, and then the movie being each frame relinquishes a different shadow. Then you look like you're flying through nothing. But then you're flying in a straight line, and what you can do is you can also add some rotation, and you're flying around, and get more kind of
Another question, if the simulation has a 400 steps, why is it only?
oh, because we don't write, because we don't make an output every step. There's not much happening between each step. I think in the there is the parameter file, whether it's called something. Yeah, this one. In the snapshots here, we say what is the first snapshot and how many times, so this is the change in the scale factor between each snapshot. So if you make that number, this number here smaller, you can also just write out even more. And you just need a lot of this classified. So this one is, so there's, these are very simple visualization tools. There is another tool which is called Paracube, which is a tool we use in many all kinds of simulation. It's like it's very powerful to visualize data and so on. And it reads in this file so that you can understand what the simulation is like. So it's a big software package, and you can take that file and you can understand the structure and you can play it. It's not a very easy tool to use. It's very powerful. But it's not easy to learn. Yeah, something like that. Software, pretty much. Now, what yeah.
We can set the parameters. I was seeing the program and see for or
So they can do both pretty much the same thing. So CAM has existed for a very long time. Very old piece of software. When the blank substance was worried completely independent software that does the exact same calculation, to verify, and it is mostly the same answer, and you are happy that now I don't know, I know how to use class, the one I use is class, but they do pretty much the same thing. They're just written in a different way. They solve the same thing. Not the same form, the same idea, the same, solve the same element. But imagine it's different. So there's no design. It's just pure prediction. But the idea is that you can output the exam that you can compare directly to the point, something like that. Yes. Whatever. the size of the sine wave is one over 5 would be one sine wave, and then also two sine waves. It's the size of the different sine wave that we are. Yes. Oh, it's not a problem. It's so when you simulate gas, you have to assume something about the equation of normally, we write Swift snapshot, right? Equation state. But here we don't have the gas, so we don't write that. And so the script doesn't want to assume, even though it's not using solve as well, we do that. So it's just that you, just I guess it's fine for that.
Yeah. But and this was simulation. Why? I don't know anything about words, but. Okay, so because I was trying like to implement this code,
Okay. What I usually do is write out the PNG files and combine them.
where?
Oh, in the Python here? Right, so whenever instead of showing the image here, you can do plot.save fig or something.
Oh, okay. Same old.
Save all of the figures and then use it for whatever you like to combine all of them.
Okay.
That's the lazy, yeah, it's the lazy way. That's the way I know.
This is like.
No, you can install it if you do apt-get install and stuff like that, it should be there. Yeah. Dashkit. Anything you use to Okay, so I've seen some of you already making images of the simulation. Looks quite cool. Now, if you make some movies, that's also fun. If you make some cool movies, just send them to me. I'd like to see what you do. Or you can come and show them. Now, like I said before, making images is fun. I mentioned we can look at the power spectrum if you want to compare the simulation to the data, which is what the script at the end here shows you how to do. So all that has happened here is that in the code, while the code was running, we calculated the Fourier transform of the density field, and it's already given you in a text file. If you don't want to do this, you could take the snapshot take all the particles and then calculate the Fourier transform of the positions. Like we have to start, we did the Fourier transform of this Gaussian random field. You could do the same thing here with all of the snapshots, just go forward. So it's already done here. The other thing that, so if you have run the updated version of the script that I put last night, you will have run the code with something like FOF in the command line. I've seen some of you have done that, and maybe some of you have not. So what does that mean? FOF means friends of friends, and it's an algorithm that tries to identify halos or clusters or clumps. It's nothing. So it is used a lot in simulation in astronomy, but it's a very general thing. People use it also for things like Facebook, for instance, where they're trying to suggest new friends. They look at the network of friends and say they try to find clumps of people that should be connected in some way, right? It's a very general algorithm trying to connect data points. And so here it's used in the simulation code as well. So we run it every so often, and it tries to calculate, are there any regions of space where there are lots of particles? If there are, we will call this a halo. Yesterday we did simulate just one halo, but there are many, I think there are thousands of halos in this simulation. If you look in the directory, when you run the simulation, there should be either a FOF directory or FOF underscore output. I forgot the exact name I gave it to it. And in there should be some files, which are HTF5. And if you open them with H5Py or any of your favorite tool, you can find it's going to be an array of halo masses. And I told you this morning, another way you can compare a simulation to the real universe is counting how many halos of a given mass there are, and that depends on the specific cosmology you choose. So for instance, here, what you do is take these files that contain the list of all the halo masses, and then just make a figure of how many halos there are as a function of their mass. And you can do this at different redshifts, for instance, or you can do this, and if you had initial conditions for different cosmologies, we could do a comparison for different models and see how they change. Another problem. Solved one, found another one.
We have here the Swift.
Yes. So when you did configure, you should be wherever you did the configure thing. Yes, we should configure and also add enable function. So /configure and space -- enable enable. Get dash false. Small letters.
There's the make file again.
Then make, and then you should now be happy to make -J5, 4, whatever. Make, yeah. Then that should not work.
And I have to replace this Swift.
Yes, you have. No, if you copied it, yes, you have to replace it. Yeah. Can you just, what's the you show me the content? You just copy that file, that line in the If you want to run this off, yes. If you want to run it, yes. If you don't, then we should do it. If you don't want to use the other. You don't have to. I just added it to the script. So the idea is that this is another way to how we compare the simulation with the universe. Maybe not. But I'll do one thing. Just counting the number of right, so this is just this algorithm while the simulation is running. It's like I found here's a halo of this mass, there's another halo of this mass, another halo of this mass. And it just makes a list of all the halos in this file. You do is you can plot how many halos there are, how many mass in that simulation. Well, that's what was solved. So that was solved. No, yeah, I agree. Oh, you run the book. So GSL is also active. So nothing was installed. Okay. So what is it? Because you've already showed me that for something else. And you ask. No, not that. No. Okay, so you're also missing. I don't know why this computer is missing it. It's so bad luck. We can check. Change, sorry. Okay, so here, in this case, I didn't give you a script to make a question. But if you look at the files up in the script, it says that generating code for monophonic. And that is a code where you also use the cosmology parameters. And then you also say how many particles we have, how many particles we want, what is the size of the box. And it will generate the file. But yeah, that's too much. Right? That code itself uses class or can. So they all rely on each other. So this is code called monophonic that brings the initial conditions. Itself is say, oh class. What is the box spectrum? And class is the box spectrum. And this one code that generates the based on yeah. It's not very difficult to do. Just people work. But if you look at it, you can check it. You can try it.
Yeah. Thank you.
Please. Looking forward to it. Choose good colors. Yes. Yeah. So, yeah, when you configure it, you should have with this. You did? Can you go in the direction where you configure? Okay, so let's do this just to configure it without the. Both activated, yes, right. So that would make.
Where you are now?
¿Será que
Yeah, the number is just. If you have 4 CPUs, that's faster. That's what that's. Well, it depends where you are now, so I don't know if that's. This is the right executable, yes. That's the there. Yes, that's fine. So then, yeah, that's correct. Just go where you're running. Simulation. You can do less, submit a message. Less.
Aleluya.
Yeah, enter. Yeah, okay, so that's running what you want. Okay, that's fine. Good, yeah. Good. Then we'll flash submit. Working. Did I like it?
Eso lo tengo que encontrar un poco. Buscar un titular se tiene que pegar bien pegado.
I've never seen that ever. No.
¿Por qué?
I don't know why.
Pues es local, ¿no? Pero vale la que dice.
Oh, yes. Yes. What do you tend to? What do you? Is that the normal script or did you change something? Can you change something to the code or what is different?
Lo que sí puedes hacer, lo que sí puedes hacer es hacer lo que
It's working for everybody else.
tiene una función.
Tiene el campo de visión.
So there's something strange with your
Básicamente.
fighting installation. Or the holding installation. It doesn't seem to have something mentioned instead of like, I don't know what it is. Not like
Porque se hace es lo que no se preocupa. No está calculando cuál es la probabilidad de que y el tamaño de la parte en el efecto de potencia, como cada vez inverso de la escala, usted está preguntando cuál es la frecuencia con la que no se entonces también entre comillas haciendo la estadística de las proporciones del flujo de la masa. Por eso el espectro de potencia en el campo coseno le daba plano, porque todas las potencias tienen la amplitud. Pero cuando usted cambia eso, estos elementos son de escalas como cada vez más chiquitos. Uno puede hacer escalas más chiquitas. Y se hacen públicos porque realmente las ecuaciones están mucho poco necesitadas. Pero en el caso real, realmente la función se puede transformar. Lo que está viendo es esto, la frecuencia de una escala más alta de la frecuencia. Hay grandes, hay chiquitos, hay grandes, exactamente. No piensen en K, piensen en el inverso de K. Realmente, físicamente, el número de datos como claro, no se significa más.
something in one of the libraries that is here that is not exactly the same. That's what I think. Depends on the speed of the random number. Some people computer just works, and some of the other machine do the same thing.
Because they use the scripts and somehow
Pretty much.
nobody's gonna leave.
My passport number? No, it's looks nice.
¿Qué línea es? Que nos publica.
But yes. Okay. So the units are 10 to the 10. Oh, I don't know. Can you open the parameter file? There's something called the parameter Cosmo something. Yeah, this one. So the unit mass is 10 to the 10 solar masses. And then what do we do? Oh, good question. Why? Okay, so first of all, what I would do is make a log of both sides. Because there's a lot of small results for now. They're all the same. If you make a big set and log size, you will see much more interesting.
Or both.
At least big sets, but I think both will be better. And then you can ask me the question.
Okay.
Hay una que está en pie y otras son perfectas. En MP, por ejemplo, una librería que se utiliza para el este que no, está por el puedes estudiar los problemas. No, tengo problemas con el
Yes. So 10 to the 13. Not every hero has the same mass.
So in the book, like the heroes are smaller.
There's one the Milky Way lives in the halo, which is about 10 to the 12 solar masses. But they're much bigger halos versus a galaxy. They're much smaller dwarf galaxies.
But they tend to be smaller than our the heroes are smaller than our Milky Way dark matter.
In the simulation here,
Yes.
many of them will be small, but some of them will be bigger. If you make the log. Okay, so I don't know. So if you have tried, so if you make what I mentioned, so if you look at these halo files, you should be able to make a histogram of the. So this is not in the script, but it's just a file, just a text, like almost like a text file. Should be able to see the number of halos in the simulation. And so if you can do one of the classic plots, which is to plot the halo mass, so m halo here, and because it's astronomy, we always do log. And then on the y-axis, just the number of halos, would be the number of halo as a function, number of halo over given mass, and then divided by the volume or something. And then what you should see, although the simulation is pretty small, so you're not going to see a whole range of this, but it should look like that. It's first has a slope here that goes as m to the power 0.1, sorry, -1, and then it gets exponential on top of. Okay. So then there are two questions here. So one is, and I guess you already know the answer because you just looked it up. But so we live in the Milky Way. Do we know what mass of a halo the Milky Way is? Any idea?
What a shame.
Okay, what is the stellar mass of the Milky Way? How many stars in the Milky Way?
10 to the 11 power.
10 to the, yeah, that's a bit more right. Yes. So typically, you think sort of the measurement for the stellar mass of the Milky Way, so it's about 6 times 10 to the 10, which I guess, yes, would be 10 to the 11 stars, that sounds about right. So that is the mass in stars. The mass of the halo, typically you can, as a rule of thumb, it's going to be about 100 times more. It's a bit less here. So the normal number people say for the mass of the Milky Way halo is 10 to the 12. So about on this curve, so it's before the break. So in the simulation here, there should be a certain number of halos that have a mass of 10 to the 12. I don't know how many exactly, maybe it's a couple of hundred, I think. Maybe a few tens. So that if I put the Milky Way here, that should be 10 to the 12. And then if you go further, then you end up in like galaxy clusters. If I ask what is the mass of a galaxy cluster, an idea, just for scale for the halo mass.
10 to power 12.
But that's the Milky Way.
Ah, okay. The cluster.
Yes.
That's the volume.
No, the whole galaxy cluster. Well,
10 power 9.
well, it has to be bigger. Right, so if one Milky Way is 10 to the 12. If you take a really big galaxy cluster, like the Coma cluster, Perseus cluster, it has 1,000 galaxies. Right? So just hand wavy, you can say clusters would be about 10 to the 15. But now the simulation we have done is much too small. There will be no big galaxy clusters. We have only done a small region of the universe, and these are very rare regions. So we will not have. But there'll be a lot of small halos in the simulation. So if you should, I think, I forgot the exact number, but we should be able to see from the simulation something like this part here of the plot. I'm sure we can get from the just plotting the number of halos that you have. Now, if you run, if you did simulations with different cosmologies, if you say I change omega matter, right? So if I put more matter in my universe, there'll be more regions that will collapse. So quite naturally, what we will see is that this function just gets higher if I make omega matter larger. And if I change the amplitude of fluctuation, which people often call sigma 8, then I'm going to make halos. I can also change the position of this break. I can make this, cut off earlier. So that would be one of the tools that people can use to compare, again, observations and simulation theory. Good. I think we have reached 4. You can keep going, of course. You can make more simulations. As I said before, if you have made some cool movies of the simulation, I like to see them. Just send them by email or just show them tomorrow. I'm very happy to look at what you guys have done. And otherwise, see you tomorrow morning.
Thank you.
So? That sounds about reasonable. What you should do is your big area. Obviously, just